So we start the last part of our chapter about group cohomology, and it is called central extensions. So we will see how group homology and cohomology helps to study central extensions. What is central extension? Let G be a group. Central extension G is group X with epimorphism from X to G such that the kernel of pi lies in the center of X. So if we denote the kernel of pi by A, then we get a short exact sequence A X G, and the fact that this is a central extension is equivalent to the fact that the induced action of G on A is trivial. Central extension if the induced action of G on A is trivial. If A is an abelian group, yes. So the induced action of G on A is exactly the conjugation by elements of by the lifts of elements to X. And if it's trivial, then this means that the conjugation by any element of X acts trivially on A, and it is equivalent to say that A is in the center of X. So central extensions of G by A. This central extension of G by A is the same thing as central extensions pi from X to G such that kernel of pi is A. are parameterized by the elements of the second homology of G with coefficients in A, where the G model structure on A is trivial. Well, and by next one, by the universal coefficient theorem, we have a short exact sequence. Well, it is split short exact sequence, but it's not important because splitness is natural, so it's difficult to use it. So it is next. Well, not exactly by universal coefficient theorem, but by the corollary that we have proved using it. X z from. So here it has to be h1 of g z, yes, but it is the same thing as g factor gg. So as a millinization of G to A H2 of GA, and here from over Z from H2 of GZ to A. Yeah, so central extensions of G by A are in some sense can be, all central extensions can be constructed using such things and such things independently. What's this? But these things depend on A, but not so difficult as this. If you know this that doesn't depend on A, yes, we can calculate it using G only. And this, then this one is simply short exact sequences of modules, and this one is simply maps, homomorphisms. So now central extensions x by g and x prime g so morphism from such central extension to such central extension is a homomorphism of groups B alpha such that alpha pi prime alpha is equal to pi, so it's natural. Yes. G x prime G square has to be commutative. And so two central extensions are called isomorphic if there is morphism from one to another, which is isomorphism, yes. So we want to classify in some sense all central extensions of G. Not all central extensions of G by A, but something like to be able to handle in some easy way all central extensions of G. And sometimes it's possible using so-called universal central extensions, which is defined in the following way. The extension, the central extension, x by G is called universal if for any central extension x prime by prime G there exists unique morphism of central extensions. Well, if we have a central extension, universal central extensions, then all other central extensions can be described using it because they are parameterized by morphisms from X to somewhere that preserve G. Well, we will see this a little later. In what sense? So the question that we want to solve is when G has a universal central extension. This question is answered in Weibel's book. We will answer it too, but we'll use a little different proof. So, first of all, let us remember that the group B X is called perfect if X coincides with its commutator subgroup. And the first theorem that we will prove about central extension is the following. This theorem allows to recognize central extension. Not central extension, universal central extension. The extension, the central extension. A G is universal if and only if h1 of x z is equal to h2 of x z is equal to 0. So it's the first application of homological algebra, of group homology in this question. Yes. Sorry. Yes. So first, let us show that if this extension is universal, let us first consider the case where this guy is non-zero, yes? We have to show that if it is non-zero, then the extension can be universal. Suppose that we have showed before that the first homology of x with coefficient in z is the commutator, the abelianization of x. Yes. So, in fact, this equality, that first homology is 0, is equivalent to say that x is perfect. Yes. So, suppose that x is not perfect, then the extension can't be universal because we don't have uniqueness. Then we have a non-trivial homomorphism. From x to some abelian group B. Yes. In fact, we can take B equal to x factor xx. Let be phi. Yes. So let's consider the central extension b times g to g. Or here we simply take the projection on the second coordinate. Yes. Then the map from x to b times g that sends x from x to 1b and phi of x, yes, and the map from x to b times g, it sends x from x to sorry, not phi, pi, to phi of x and pi of x. Amorphism of central extensions. Central extensions. And since phi is non-trivial, we don't have uniqueness. And hence x pi g is not universal. From here until the end of proof, we assume that x factor xx, which is h1 of xz, is 0, etc. that x is perfect. Well, first of all, we will prove the uniqueness. For this, we don't need the fact that the second homology of x is trivial. The perfectness of x already guarantees the uniqueness in the following sense. If x is perfect and x by g and y x prime pi prime g are central extensions, then there exists not more than 1 morphism from X to so if by some reason for any central extension we will have a morphism from this central extension, then it will be universal. So in some sense, the perfectness of X is equivalent to the uniqueness property of to the uniqueness part of universality. So well, let us first write the remaining part of extensions, yes. And suppose that we have two morphisms, two homomorphisms. From X to X prime, let it be phi and psi, such that phi prime phi equals pi equals to phi prime psi. Then there is some map gamma not there is. Let us define gamma of X by the equality phi of X is equal to pi prime of X by gamma of X. Yeah, so gamma of X is something like pi prime of X inverse multiplied by pi of X. So gamma at this moment is a map from X to X prime, but since here phi and psi, of course. But since after application of pi prime we get phi of X, which is pi of X, is equal to pi prime psi of X, pi prime gamma of X, and this again pi of X. We have pi prime gamma of X equals 1g for any x, and hence gamma is a map from X to A prime, because A prime is the kernel of pi prime. Well, and moreover, gamma is homomorphism, because if we take x and y then and put here, then we get phi of xy, which is equal to phi of x, phi of y, which is equal to psi of x, gamma of x, psi of y, gamma of y on one hand, and on the other hand psi of yx, xy, gamma of xy, which is psi of x, psi of y, gamma of xy. And now, since we have shown that gamma is mapped from x to a prime, then gamma of x lies in the center of x prime, yes, because this extension is central. And hence we can cancel this and this, because they commute. And so we get that gamma is a homomorphism. So we got a homomorphism from a perfect group to an abelian group, and you know that such a homomorphism is trivial, yes? Because any homomorphism from a group to an abelian group factors through abelianization, and the abelianization of a perfect group is trivial. Then gamma from x to a prime is a homomorphism. Then gamma of x is equal to 1 a prime for any x from x. And this exactly means that phi is equal to psi. So we have shown that if there is some morphism from extension x pi g to some another central extension, then it's unique, and so it remains to understand when for each central extension there is a morphism. And what is stated in the theorem is that it's true if and only if the second homology of x coefficient z in z is trivial. So since h1 of x z is 0, by universal coefficient theorem we have h2 of xa of ga, yes. No, xa, yes, is isomorphic to hom over z from hom from h2 xz to a. So, in fact, h2 of xz is equal to 0 if and only if any central extension of x splits. So for any y, let us call it rho x such that kernel of rho lies in the center of y, one has y x isomorphism here kernel of rho times x by 2x. Yes. This commutes. Here we have direct product because, if this is 0, this means that it is always semi-direct product, but since this central extension, the action is trivial, so it's simply a direct product. Yes. So any central extension is isomorphic to the direct product extension. If and only if this is 0, so it's equivalent to the fact that h2 of xa is 0 for any a, for any trivial x module a, and this is equivalent to this. Because this parameterize central extensions. So it remains to prove the following claim. Suppose that x is perfect, then x by g is universal, if and only if any central extension of x splits. Well, first let us prove from the left to the right. So suppose that the extension is universal. Well, suppose that b x tilde rho x dy is a central extension of x. Well, let us prove that. So, what also we have pi here, yes, 2g. And so we can take the composition. It will still be a an epimorphism. So let's prove that the kernel of pyro y g is a central extension. So we have to prove that the kernel of pyro is in the center of y. So let us pick some element in the kernel of pyro. Let it be z. And we want to know if it commutes with everything or not. So let us consider the conjugation by z. So we pick y Okay, let's consider first new z from y new z from y to y. That sends y to z y z minus 1. Yes. And we want to show that new z is trivial. Okay. Sorry. Okay. Okay. I don't think we need to use it. So define gamma of y for y from y by the equality z y z minus 1 equals to y times the gamma of y times y. Yes. So let us first apply rho to this equality. Yes. Then we get rho of z, rho y, rho of z minus 1 equals to rho gamma of y, rho of y. Yes. But since pi rho of z is equal to 1, rho of z is an element of the kernel of pi. Yes. So rho of z lies in A, which is in the center of X. And hence everything commutes here, so we can cancel this and we get rho gamma of y equals to 1 x. So gamma is a map from y to where? To B. Yes, because gamma of y lies in the center, in the kernel of rho. Well, since B lies in the center of y, we have Vz xy z minus 1 is equal to gamma of xy yes. And on the other hand, it is since the conjugation is homomorphism, it is gamma of x, gamma of y, and since gamma, the image of gamma is in B and B in the center, we can commute, and hence gamma of xy is equal to gamma of x, gamma of y. Hence, gamma is a homomorphism from y to B. And finally, this homomorphism is trivial on A, on B. Gamma is trivial on B because B in the center is in the center of y, and hence induces homomorphism gamma prime from x to b. Yes, such that gamma is the composition. But again, x is perfect, b is abelian, and b is abelian, gamma prime is trivial, hence gamma of y is equal to 1 b for any y in y, because it's simply composition. And this means that z y z minus 1 is equal to y for any z from kernel of pi rho, because we take an arbitrary z for any y and y. And this exactly means that the kernel of pi rho lies in the center of pi. So this map pi rho to G is a central extension by we also have our universal certain extension, and by universality there is a map here. That is denoted by theta, such that everything I need. So we have now what? We have pi theta is equal to pi, yes. And what do we want? We want to show that rho theta is identical, yes? How to show this? Again, the same trick that was already done 2 times. So we have rho theta of x. Since after application of pi we have the same thing as on the x, then it is x times gamma of x for some gamma from x to a, yes, because this gamma of x has to lie in the kernel of pi. And again, using the fact that a is in the center of x, we can show that gamma is a homomorphism. Again, gamma is a homomorphism, and hence gamma is trivial. Hence, rho theta of x is equal to x for any x from x. And this exactly means that the central extension rho splits. Thus, we have shown that if the central extension is universal, then the second homology of x with coefficients in z is really 0. Yes. So it remains to prove our claim in another direction. Suppose that any central extension of X splits, and let us prove that then this central extension is universal. So we have, let's pick some central extension. B, Y, G. Then we can use pi here to construct another central extension. So it's pull back in the category of groups. If you want to have a more explicit construction, then you can define P as a set of xy from x times y such that below again, yes, such that pi of x is equal to rho of y, something like this. Then this map is simply projection of the second component, this map is a projection of the first component, and this map is this inclusion and then inclusion to the second component. And everything is well defined. You know this. And so you get here an extension of X by B, and it is again central extension, yes. First of all, you can use this explicit construction to show this, or you can understand that, in fact, the action of X on B is induced by this morphism, and since it goes through the action of G, it's trivial to something like this. And so there is a map from X to P that splits this extension, and we claim that that would be something like pi prime, that X, so here we go pi prime sigma is a morphism of extensions. Why it is a morphism of extensions? So this composition has to be equal to pi, yes. But if we multiply it by this So let's prove it. It's not very difficult. So we need that rho pi prime sigma is equal to pi. Yes, it is equivalent rho prime. Yes, it is equivalent to the fact that rho pi prime sigma rho prime is equal to pi rho prime, which is by the commutativity is simply pi prime rho pi prime. So it's equivalent to the fact that, sorry, well, how to explain this? One moment. Okay, that's not right. Equivalent simply if we have some element x in P, yes, then sigma rho prime of x is equal to x times x prime, where x times b, where b from b, yes, because when we apply rho prime, we obtain the same thing, yes. So rho pi prime sigma rho prime of x is rho pi prime of x b. So it's rho pi prime of x, and rho pi prime of b it is simply rho of b, yes. So we multiply 1, so it's rho pi prime of x, because b lies in the kernel of rho pi prime. Okay. And so we are done. So now we have corollary. Let's say that if G has a universal central extension, then G is perfect. So it follows from the first part of our theorem, if x pi G is universal. Central extension. Then X is perfect, and hence G is perfect. Oh, it's clear that if a group that homomorphic image of a perfect group is perfect. So suppose now that G is perfect. You want to prove that in this case there exists a universal extension of G. By universal coefficient theorem, we have a natural isomorphism. H2 of GA, natural in A. Is isomorphic to hom over Z H2 of GZ to A. Well, let us understand what does mean naturality of this isomorphism. Well, what does it mean? Neutrality means that if we have another group B, yes, then and a morphism phi from homomorphism phi from A to B, B another abelian group, then here we have H2 of G phi to H2 of GB. Yes, here we have isomorphism of this, and here we have hom over Z GZ H2 GZ phi. And this square commutes, it's neutrality. But what does this mean? This means that if we have some central extension, yes, and suppose that it corresponds to a map gamma, for example, from H2 of GZ to A. Yes. Then, when we go here, what do we get? We get H2 of G phi of this central extension, and it is central extension that can be obtained via push out. So this central extension corresponds to what we get here, yes? And here we get this thing phi, and it is simply a map to B, which is the composition. So now if we take A equal to H2 of GZ and gamma equal to identical map on the second homology, then what do we get? Here it's the diagonal maps, so here it's phi. So this morphism phi corresponds to some central extension of G by B. Yes, such that there is a morphism phi here from and this this central extension with some fields, fixed central extensions corresponding to the identical map on the second homology of G. Yes. So what do we get? We get that if we take some central extension of G by some B, then it corresponds to some map from the second homology to B. And in fact, this map gives this diagram. Yes, so for any central extension, we get a morphism from this central extension that corresponds to the identical map. So we almost have shown that this central extension corresponding to the identical map on the second homology is a universal central extension. So for any central extension B x tilde G, there exists map from here to here. well, it also well, and since this correspondence is one-to-one, yes, so for each morphism there is exactly one central extension, then phi is uniquely determined by B x tilde G. Oh, sorry, 1 minute. Oh, okay, we have shown that for this extension, yes, for any other extension, there is a morphism. So it remains to show that this morphism is unique. As we have told before, it's equivalent to the fact that X is perfect. To show that X is perfect. But if X is not perfect, then there exists non-trivial homomorphism from X to A. That is denoted by gamma. A abelian. Then we have commutative diagrams. Well, first of them is A times G, here G, here H2 of G, A, here X, and here, let's do not this pi, yes. So it is 1a pi, and here y and a. Yes, and another one is H2GA, and this one by what? Here ut x by G, G, A times G, A, here it is gamma pi, yes, it is still commutative, and here it is gamma yot. Yes, and we again have commutative diagram. So, since this correspondence is one-to-one, yes, for each map there is only for each central extension there is such diagram, and phi is uniquely determined by the central extension. And here we have the same central extension. Then gamma iota is equal to 1a. So this means that gamma iota is trivial, and so gamma is equal to gamma prime pi for some gamma prime from G to A. Yes. But G is perfect. Perfect. Gamma prime is 1a and has gamma is 1a, and this contradicts to the assumption that gamma is non-trivial. So finally we have proved that the existence criterion. And so our last theorem that we have already proved in this section is that G has a universal central extension if and only if G is perfect. And in this case, the universal central extension is the extension of G by the second homology of G with coefficients in Z. That corresponds by the universal coefficient theorem to the identical map on H2 of GZ. So our next chapter is Hochschild. Sorry. Homology. So what we have studied before is the beginning of the homology theory of groups, and Hochschild homology is the homology theory of algebras. So from here on, we fix some commutative ring K, and all that we will consider will be K algebras. So A always will be K algebra. And also we will write simply tensor instead of tensor over k. So what is K-algebra? You know, yes? It's like K module that has a structure of a ring. It always has 1 by our assumption, the unity. Then K can be, then there is a map from K to A that sends alpha to alpha times 1, so on. So in particular, yes. So, definition. Bar dot of A is the complex defined by the equalities. Bar n of A is simply A tensor n plus 2. And dn from bar n plus 1 of A to bar n of A is defined by the equality dn of A0 tensor A n plus 2 is equal to the sum for I from 0 to n plus 1, 0 tensor I plus 1 tensor an plus 2 and multiplied by minus 1 in the ith power. So it's very similar to the bar resolution that we use to compute group homology. Not to compute, to study. So what? Note that bar n of A has the structure of A by module defined by the equality A0 tensor plus 1 B is equal to A0 tensor plus 1 B. So we simply multiply on the left term and on the right term. And Gn is a homomorphism of A by modules. we have also the map mu from bar 0 of A, which is by definition A tensor A, to A that sends A tensor B to AB, and it is a homomorphism of A by modulus 2. Moreover, mu gives a map of complexes, a morphism of complexes, which we denote by mu2 from bar A to A, where A is a complex that is concentrated in degree 0, of course, and to see that it's a map of complexes, we simply need to check that mu d0 is 0, so we have to take C, then we will see that it's mu of AB tensor C minus A tensor BC, it is ABC minus ABC, it is 0. So bar dot pretends to be a resolution of A, and now we will show that it's really has all exactness properties that are required, but the problem arises with projectivity. So it's not a projective resolution in general. Well, I think that the next time I will formulate the next lemma. Now let's finish.